Welcome, everyone. Thank you for joining us this morning or whatever time it is where you are, for the newest installment of the IEEE Computer Society's Quantum Insider webinar series. Today, we have choosing the right time and steps to start working with quantum technology. And our presenter today is Doug Fink. Doug is the Chief Content Officer at Global Quantum Intelligence, GQI, and the Managing Editor of the Quantum Computing Report by GQI, which he founded in 2015 as the first news and analysis website dedicated to quantum technology. He brings a broad range of experience to help explain and accelerate the adoption of quantum computing in the broader marketplace. Doug began his career as a mainframe computer design engineer at IBM, and later held various executive roles in marketing, engineering, and operations at Intel, Western Digital, Corning, and several startups. He has degrees in computer engineering and management from the University of Illinois Urbana-Champaign and MIT, respectively, and holds 8 patents in the field of computer technology. The way we'll run this today, it's being recorded, so we will post it afterward. You can submit questions along the way using the chat feature, and we'll grab those after the presentation. And you will be receiving updates to let you know once the recording is posted online, as well as to let you know about future installments in the series. And with that, I pass it off to Doug. Thank you.
Okay, well, thank you, Steve, and good morning, everybody, or good afternoon, or good evening, wherever in the world you are. Let me start. Just quick update on our company. Our company is GQI, Global Quantum Intelligence. We actually formed through the merger of 3 independent analysts who were following the quantum industry. As Steve mentioned, my original firm, the Quantum Computing Report, I started in 2015, really when no one else was reporting on it. It was sort of a research backwater at that time. Now we're a worldwide organization with over 20 employees. We service various industry leaders, the tech majors. We've worked with vendors. We do a lot of work for various governments, U.S. government and other friendly governments, and we do investors. One of the things we do a lot of work in is due diligence. For a lot of the deals that you've been seeing, a lot of the investors will come to us and say, look, we want a deep dive into their technology, how good it is, and we've done over 30 of those types of projects with potential value of over $2.5 billion. So we are worldwide. So we have people, I'm based here in California. We have people on the East Coast in DC. We have people in Europe, in the Middle East, India, and we have an affiliate in Japan. So we know, and we know almost everyone in the industry. And we have very, very deep contacts that we've been working with some of these folks for years. We are a member of the Quantum Economic Development Consortium here in the US, and we're also an affiliate member with the Quantum Industry Consortium in Europe. So, we work with both of those organizations. One of our secrets, one of the things that we're very proud of is that we have been collecting data on the quantum industry since for the past 15 years, or past 11 years. And we have put it all into what we call a GQI data warehouse. We have gigabytes and gigabytes of information related to anything you'd want to know about quantum, organizations, use cases, investments, what governments are grants, all that type of stuff. And then we do have it available to our clients in what we call a GQI intelligence portal, where people can go in and query this. We have tied our database, our data warehouse, to an LLM, so someone can actually ask questions of the LLM, and it'll answer it based on the training information that we provided based on our things. Since I started the Quantum Computer Report in 2015, we have posted over 3,500 articles about the industry. All of those are in the database, as well as much, much more information. Just a little bit about our company. Let me start, and I'm going to start talking about the thing you should do before you start working on quantum computing. One of the things that we are very concerned about is the fact that a powerful quantum computer using an algorithm called Shor's algorithm will be able to break the RSA encryption that has been the standard in the internet and in industry for the past 20 years. Um, and it seems like every year the computers get more and more powerful and the algorithms get more and more efficient. There was just a posting about a month ago about a company that says that they can break or run this Shor's algorithm with only 100,000 physical qubits. And that is well within the reach of roadmaps of people who expect to have that level of quantum computer within the next few 5 years or so. The other thing that people should be aware of, there is an attack that people have called Harvest Now, Decrypt Later, where the bad guys will be able to, they can tap into your lines right now and store your information. Even though it's encrypted, they may not understand what it is, but they'll save it on a hard drive. And they'll save it on a hard drive for 5 years. And when those powerful quantum computers are available, they will be able to break it. So any type of data that you might have that has what we call a long shelf life, that could be vulnerable to those types of attacks. So if you are in an enterprise, and that's what I'm targeting this too, is end users and people in enterprises, you need to start your quantum safe efforts right now. And of course, we can provide some additional assistance. There are a lot of vendors who are starting to work in this area. There are algorithms that have been approved by the National Institute of Standards and Technology, and there have been executive orders from both actually Presidents Trump and President Biden for the U.S. agencies, for the government agencies, to be able to make your IT systems what we call quantum safe. And that's shown here in this chart here called the CNSA timeline. So the cost of failure can be very, very high. Could be in the billions of dollars for large companies. And our recommendation is if you haven't started it now, you need to start it immediately because it is a long process. Some of these large organizations may have thousands of programs and thousands of servers that need to be upgraded. So it is not an easy thing to do. And some of you in the audience may be familiar with Y2K. I would call this, sometimes people call this process Y2Q, years to quantum. And I would say Y2Q is like Y2K on steroids. So very important that you pay attention to this. Okay, now let me turn to quantum computing. I'm sure everyone has seen all the notes about all the announcements. There's certainly announcements every week about new hardware providers that they have a new record in terms of the number of qubits or what we call the fidelity of qubits, how accurate the calculations are. The industry is expanding the capabilities of the hardware is expanding on an exponential rate. But at the same time, what may not get as much press, but is equally important, is that the algorithms are getting smarter and smarter. People are figuring out ways of developing more efficient algorithms to be able to make the calculations with fewer numbers of qubits or use error correction. So there's a lot of work there. We report all of that on the quantum computing report in our daily newsletters. So the advance of the industry is amazing. When I started looking at quantum 11 years ago, state of the art was 5 qubits of a machine that IBM put online in 2026. And now people are putting machines online that have hundreds of qubits. And again, more than Moore's law, doubling or even more than that every year. So this what I show in this chart here is the fact that there is going to be a lot of value created through the adoption of quantum computing. In much the same way, a lot of value, of course, was created when people started using the internet. They the value per year, and we think it's going to exceed $1 trillion by 20 in the next 25 years. It will grow as you see in this chart here, but I would point out that that value is reflected in two ways, in two fundamental segments. The quantum industry itself, the providers, the companies that provide the quantum computing and the software and the services, of that $1 trillion or so, they will take perhaps about 30% of that, primarily in the form of revenues. But the end users, people who will be using this, and you can see some of those industries in the blue square on the right, they're actually going to achieve the bulk of the value through an introduction of new or improved products or being able to reduce product costs. So think of a pharmaceutical company, for example, that might spend $100 billion or $100 million, with the quantum computing companies, in cloud services or buying quantum computers or whatever. But they develop a drug, and that drug sells $1 billion per year, which many drugs do. You're going to see end users are going to really, really benefit from quantum. So that's why we're giving this presentation today, is to number one, show folks that there's going to be a lot of value there, but at the same time, talk about the process of how you do that, because you just don't turn it on overnight. And following in the rest of this presentation, I'll show you some various steps that our company recommends to people in order to start a quantum program and achieve that value. So first I want to talk a little bit about a study that we've done. We call it a use case categorization study. Every company has various types of problems that they need computers to solve. And what our study shows, and I'll show you just a glimpse of some of the results of that study in this next few slides. What are the most promising use cases for that? The thing that we always talk about when we talk with end users is if you have a specific problem, you may have a way of solving it with a classical computer or using AI, and you may solve it with quantum. And you need to figure out, which of those use cases would be best continuing with classical approaches or AI. We call AI as classical, or you want to move to a quantum. So the reason you want to move to quantum is because there are some problems, like Shor's algorithm, breaking the encryption, which involves factoring a semi-prime number, that is intractable with a classical computer. Even if you had the largest data center the size of Alaska, it would take millions of years to do that. There are quantum algorithms that we know about that we think, again, in about next 3 to 5 years, we'll be able to solve that problem. So there's intractable problems. There's problems where it's just plain faster. Maybe you could solve it classically, but it might take a month of classical computing versus 2 minutes on a quantum computer. Or problems where quantum computer can do it more accurately. Computational chemistry, like simulating drugs, for example, is an area where people do it classically, but they have to make approximations to do that, and they may not get the exact answer. And quantum computer is something that could give you the exact answer. So what we did in our study is we did a literature search, both technical and commercial descriptions. We have in our data warehouse. We have a library of a few hundred use cases of possible ways that you could use a classical computer. We looked at how they could compete against the classical solutions, as I was describing earlier. You also want to understand what are the resource requirements. If you are using a quantum computer, you need a quantum computer that has 100 qubits, 1,000 qubits, 10,000 qubits, a million qubits. And what we do is we have a classification for quantum computers. We also look at roadmaps for all the quantum suppliers, and we classify them by era. And the metric that we use is, we call it QOPS, quantum operations. And we have charts that will take applications and classify them in terms of kiloquops, megaquops, petaquops, teraquops. And we do have a product, and we also, as part of our study, have a market model of what the potential business potential and the value. And that chart I just showed you a second ago, this chart is a chart that was based off of our quantum market model. We can then rank each use case by several factors: the quantum segment, the scalability, the advantage, the complexity to integrate, economic impact, and the QC performance required. So just to show you, we have done that by industry. And this is just an example we do for the financial industry. The size of the bubble is the scalability potential. Some of these things, you notice around here, it's only a semicircle. It's not completed, whereas this is only a semicircle. Something like this is something that shows a competitive advantage. We do color code the integration complexity. And then these little things here, the lock here represents cybersecurity cryptanalysis. We do classify the algorithms into different types of algorithms. This here would be an optimization, sort of shown as a graph. Machine learning is shown with a picture of a head with a brain. Quantum communications, which I won't get too much into, is shown here by the key. And we also have things like there are quantum sensors, for example, quantum imaging. So we do show this across all the matrices, and we also classify these with how complex, or how, what performance level you would need in a quantum computer. Today, there are various algorithms that the post-quantum cryptography, which I just talked about a second ago, that can be implemented today, or should be implemented today. NISQ stands for near-term intermediate scale quantum. We do believe there will be a few applications that can run on the quantum computers that have maybe a few hundred qubits that do not use error correction. One of the issues we have in quantum computing is that the way the information is stored is in a piece of something we call qubits, which stands for quantum bits. They are quite fragile, actually, and they don't hold their state very long, unlike a classical bit, which can undergo millions and millions of operations before it achieves an error. Today's state of the art in a qubit for doing what we call a gate operation, the fidelity state of the art is like 99.99%, which, maybe that might sound good, but again, that's one out of every 10,000 operations are going to give you an error. And some of these algorithms are going to take millions and millions of operations. So there are many, many applications that will not succeed, will not be able to do successfully until you have what's called error correction. And there's a lot of technical work there that we report on. FTQC stands for fault tolerant quantum computing. So there's a handful of things that will you'll be able to do without fault tolerance, but there's a whole bunch of things. And over the next few years, if you look at the roadmaps, reports we have on various vendors, we see that companies will today, if you reuse a quantum computer, there's no quantum computer that you could use on the cloud from IBM or Amazon Web Services or Microsoft or any of the others that are online today with error correction or fault tolerance. But over the next couple of years, you'll start seeing those show up. So this just shows you how we rate the use cases. And we do it, again, segmented by industry, according to all these various things, whether it's sensing, computing, communications, and scaling, and how large it would be. So again, I won't go into these in detail. We have several hundreds of these, but I did want to show you that we do have these segmented by industry. I just showed you the financial services. We have one for pharmaceuticals and life sciences, cybersecurity and defense, healthcare, medical devices, telecom, energy, oil and gas, advanced manufacturing, automotive, chemical and materials, logistics, environmental, agriculture. I think we have about 12 different industry segments that we track, and we have in our database the algorithms that might be applicable to each of those things, along with these ratings that I just described. So, assuming your company is certainly in one of those segments, question comes: okay, how if in my organization, how do I figure out which ones to do? Quantum is very complex, and what are the steps I need to take? So our company has come up with a 4-step process that we say discover, decide, execute, and then deploy. And I'll talk about each of those. So if you're just getting into quantum, you want to understand a little bit more about it. You want to understand who the potential use cases are. What are the modality comparisons, whether you want to use photonic versus superconducting versus ion traps, what are the difference of those are? You need some basic understanding of how quantum would compare against AI. What do we mean by the term of hybrid quantum classical computing? What sectors are available? And again, I will talk about each of these in more detail in just a second. And once you have a basic understanding of what quantum is, then you want to start looking at your own company a little bit and figuring out where the best use cases are. How do you want to allocate your investments? What might be your ROI? Whether you want to use compute or sensing, what would achieve advantage and when you could achieve advantage. And this is a stage where you start putting your plans together to figure out which use cases you want to go after, what type of resources you need to do that. And then you move on to the next stage, which is execute. So execute, you want to develop your programs. You want to put together your supply chain strategy, figure out the roadmap. How do you enable your sales, and how do you look at the performance? How do you do compatibility testing? And then the last stage is deploy. So once you have a quantum application and you've maybe you have an innovation team that's put together a proof of concept, they've shown that it could work, to actually introduce it into your organization is is fairly complex. And by the way, it doesn't matter whether it's classical or whether it's quantum. You have to go through the same steps. So the deploy stage is pretty much the same, or the steps that I'll talk about are pretty much the same, whether it's classical or quantum. You have to integrate it with the rest of your IT infrastructure. You have to do employee training. You have to line your teams. You have to monitor it, make sure there's no bugs, and you have to see if there's any improvement possibilities in the future. So I'm going to do a little bit of deeper dive to each of these steps now, and talk about what you want to understand. So in the discover phase, what you want to do, of course, is really make sure that the problems you are solving are really the problems that are important for your organization. You want to interview your users. You want to understand the bottlenecks and pain points. Are there any problems that they have or things that they're doing where they don't even have they would like a computer program to help them solve it, but there's not one available because it's just too complex. Or there may be ones that take excessively long run times, or you're using it, but the results aren't very good. They're inaccurate. And you want to sit down with your users. You want to brainstorm a little bit about what if. And one key thing is to review usage to identify any jobs that you may be running, but they have very, very long runtime and use a lot of the classical resources. At the same time, you want to secure the basic knowledge of quantum computing. With some of the steps I talked about before, look at those potential use cases, understand the vendor landscape, who does what, who provides the cloud platforms, what type of software is available, what type of consultants are available to help develop the program. And you want to learn about the different quantum computing modalities and the strengths and weaknesses. So the one resource I would point out to you, it's completely free resources. Again, this is the website I started 11 years ago. You go to quantumcomputerreport.com, and every week we report on the new developments. We also have a free newsletter that we get sent out every Sunday. So you go to the homepage here, and you can sign up for that free newsletter, and you'll be on the mailing list. And every Sunday morning we'll talk about things. And typically we post 25 to 30 new articles about new announcements, new products, new fundings, new management, new startups that are there, and it gives you sort of a weekly update in terms of what, so you can stay current. So these are the three steps that we would recommend for the discover phase. Once you have done some discovery, then you want to look at some of those applications, some of those use cases that we talked about earlier, and see which ones might be appropriate. And you're going to think about resources. You want to think about, okay, we have an application, we think it might be applicable. There are a few ways of, you will need some resources inside the company. There's a couple ways of doing that. You may want to hire some quantum researchers, put them in, some people call them innovation teams, have small things. Finance companies may have a team of a handful of people who are developing these things. Or you may want to engage with technical consultants, contracted, and there are software companies that will provide you with applications as a service that you would work hand in hand with. And you may even want a mixture of those. You may want to certainly do an ROI in order to figure out, make sure that the benefits justify the expense. And then there are various application libraries. There's vendor libraries, application platforms, open source libraries, that there are various algorithms that you think might be applicable. And then you want to start investigating some of the potential providers. If you do want to use either technical consultants or use a web platform, Um, you want to decide on which vendor you might want to use. You want to every vendor has strengths and weaknesses, and we do categorize those for our clients. And you do want to understand what the project budget is, so that you can understand the project costs, which will include, of course, any employees you hire, any outside resources you bring on, as well as machine time, because machine time will can be costly. And then, of course, you're going to need management approval. You're going to put together the program plan, obtain your management approval, and establish the targets for performance, cost, compatibility. And during this process, you're going to create the plan of how this will fit in with the rest of your IT system. Then we get down to execute. So you've decided, what you're going to start off with. You've got management approval to do that. You are bringing on your resources, your technical resources to do that. Most companies that we talk with, they start out with what's called a toy model. If, for example, typical, a typical application, for example, might be logistics, delivery or scheduling. If you have a manufacturing plant, scheduling the jobs from machine to machine, routing traffic. Someone did an experiment of a toy model of routing buses through their metropolitan system. But you want to, if you have, let's say, a factory, and the factory has 1,000 machines and 2,000 process steps, you don't want to start at the full factory. Maybe you start with this toy model, start with routing 5 machines and 10 process steps. And you do this to test out the proof of concept, to get people interested, develop sort of the prototype system. And of course, if you start small, reduce the machine times, it'll allow you to debug faster, and you'll get quicker feedback on that. And that will allow you, once you have this toy model worked out, then you'll be able to scale it up. Some people, what they may want to do is actually run, there are different quantum computing platforms. I mentioned earlier about different modalities, superconducting versus photonic versus neutral atoms. You may actually want to try out different ones, see which one is the best fit. Some of these services, Amazon Rocket, for example, they actually are hooked in through the Amazon Web Services to 3 or 4 different quantum computers from different providers. Amazon does the same thing, and in some cases, you'll be able to try out these different ones with one line code changes. Probably the most widely used platform right now for developing programs is Qiskit, which was introduced by IBM. It's open source now, and most hardware platforms today will accept Qiskit programs. They'll translate it to their own native format if necessary. So that's a good way of being flexible and trying out different ones and seeing which one is best. And then as work progresses, you scale up to larger, realistic size models. In some cases, for example, the finance industry, for example, they may not want to use real data, user data. For example, you're doing loan approvals, for example, or risk assessments. Maybe you don't want to use real people's data, but you can create synthetic data to test out the program, and that allows you to maintain confidentiality. And using these larger models, you can test the performance, compatibility, accuracy, making sure that what you've developed works, before you actually start incorporating it. And then again, the final stages, you think you have an application, you've programmed it, you've tested it, you have your plans. Now you have to integrate it into the system. And as I said earlier, it's really the same problem as any program or any new system you're introduce into your IT system. You want to make sure that the availability, reliability, and security platform is accurate. One of the things you need to look at is potentially a service level agreement. If you're using an external cloud platform, you want to understand what their availability is, making sure that their system doesn't go down very often, particularly when you need it. And of course, you want to look at security. What are the various security protocols? Who has access to the data? You want to run tests to see how it works with the rest of your system, compatibility, performance, any side effects. And then you're going to need training. So you've developed your program and you may have operations managers or biologists or chemists who will use what you've put together. They will just see your program as a high level interface that you've done, but they're going to need training, and you're going to want to show them how to use that. And then as you deploy, you want to monitor the progress. And after the system goes into full production, you just don't want to walk away. You want to actually see, number one, how people are using it, and number two, are there any future improvements you want to have? So those are the steps. And again, we could certainly help our clients walk through those steps. Again, using all the data that we've put together. So timing is important. I will mention that some of those applications may be too far in the future. If you have an application that may take millions and millions of qubits, you may not have a quantum computer available until 2035 or so, or in the 2030s, that really can do that for you. So maybe that's a little bit too far in the future. But you may have other applications that may need machines with 100 or 1,000 or 10,000 qubits, which we do expect to see over the next few years. So as part of the decision, you want to understand that. As I mentioned, the performance is increasing rapidly, but again, today the machines that are available today only have a few hundred qubits without error correction. So that's one of the things you look at. Generally, you also want to don't underestimate how long it may take to develop an application. Quantum computer is much different than classical computing, so several of these projects may take a couple years to put together, and you may not want to start too early. If you're an IT manager, the thing you want to avoid is doing a toy model, and then after you've sold it to management, and then say, well, but I can't put it in production because the large quantum computers aren't available to 2035. So you want to manage expectations with your management. So picking the right projects that allow you to show success under the timeline that you sold management on is important. But at the same time, you don't want to start too late, because as we all know, industry is very competitive, and you don't want your competitors to get an advantage. So our recommendation, again, for anyone thinking about quantum, now is actually a good time to start that discover phase I was talking about earlier. Just understand what might be possible, what some of the time phrases are. You may want to go to the decide phase, because you think there might be something that is applicable and would fit in, appropriate for the time frame. And but you decide will help you look at that a little bit closer. And then if the side phase says, hey, we think we have something, and we think that it's the computers will be available at the same time we're developing the program, then you might want to move into execute. So every company is going to have a different journey. Their use cases are going to be different. The phases that they go through are different. But again, we think that most enterprises the discover phase is probably appropriate right now for most enterprises, and you could move on. So with that, I would say if you want to look at this further, you can send me an email. We can set up. We'll offer an end user a free 1 hour briefing, which will talk a little bit more about this in detail, an executive briefing. What I show in this chart on the left, in the bottom left, we talk about all the different platforms. And one of the things that our company does is we rate all these platforms, and we look at all the various vendors. You can see the various vendors' names there. We segment them into quantum majors, QC challengers, platform as a service, applications as a service. There are a lot of companies out there. Some of them specialize in specific areas, and we can talk about that. If you see on the left, this multicolored chart, on that chart where it says users, applications, algorithms, frameworks, architectures, control plane, quantum plane, those we rate all those companies according to where they play, whether they're, towards the top is really software companies, towards the bottom are hardware companies, and we do the sophistication. And the chart on the right is an exercise we did called a quantum resource estimation. We've taken various algorithms and we've actually programmed those algorithms, and there are tools that are available called quantum resource estimators that will tell you how many qubits you need and what the quality of the qubits. Well, again, we call it qubit fidelity, and each of those colored things shows the resource estimation, and you probably can't read that list on the right of that chart, but those are different algorithms. And we estimate how many qubits and the fidelity of the qubits, and we rank them according to different modalities. In this case, we compare ion traps versus superconducting versus Majoranas, topological qubits, which is what Microsoft is working on now. So went the wrong way. So with that, that's the end of my prepared remarks. Again, I want to thank you. As I mentioned, we've been working in this area since 2015. We do work with many companies, Fortune 500 companies, 16 governments, do a lot of due diligences, and we have millions and millions of data points. So you can see our website in the QR code there, www.globalqi.com. You can see a little bit more about the services we provide. And my email there is again, doug@global-qi.com. And if you want to learn more about some of this stuff, send me an email, and I'd be happy to help you. So with that, that's the end of my prepared remark. I think we may have a few questions. So I'm going to ask Steve to look through the chat and see what questions are available.
Yeah, so we have a couple of questions that, so the first one is, what's the percentage of FTQC in existing quantum computers? You mentioned 1 in 10,000 operations is an error. Is this the standard percentage at present?
No. The 1 in 10,000, again, 99.99% is the very best that we've seen. It goes from different vendors, and those, sometimes we call those hero measurements, the very, very best. There are some companies that are sitting at the 95% level, which means that 5 out of every 100 operations are going to fail. So it varies tremendously between the companies and the different machines. IBM, for example, I've been tracking IBM for 10 years now, and they've, I think they originally started with their original machines were like 85%. So they're 99% now. So it is improving. But that's one of the things we have in our data warehouses. We do have what we call scorecards, where we track the fidelities of those and how well they're doing.
Excellent. There's another question. Do you believe quantum compute power will be offered similar to AI GPU by vendors that allow you to use this compute power per need slash use? Any concepts on how this would be costed?
Yeah. This is available now. Again, the leading providers are through a cloud. The leading providers are Amazon Web Services, Microsoft, and there are some others that will do that, and they will cost it in a very similar way to how you cost uh, classical computing over the cloud. Time per CPU second, or actually GPU second, times per job, and each one of these companies does have different things. I believe Amazon and maybe Microsoft has their pricing online, or you could contact these companies directly, and they can tell you. IBM, I know, is also at least one of their things is online. They have what's called a pay per use, and I can't remember what they charge, but you can go to the IBM website, it will tell you if you need a lot of compute time, then you can work special deals. IBM, for example, will sign you to a yearly contract that will give you, if you need large amounts of time, it'll certainly be much lower in cost than the pay per use, the one time pay per use type deals that they have. I would also point out IBM does have a free tier also, primarily for students or maybe people doing some learning. Those are their smaller systems, their older systems. They make some limited time available for free. So if you're just getting into quantum, you might want to start looking at those too.
Question. Riverlane recently published a forecast that early FTQC will produce over 100 terabytes per second of syndrome error correction data. I've seen little data on the classical compute requirements or trends to successfully run NISQ/FTQC.
Okay. So I need to explain a little bit more about what that means, or what the question means. So I talk about fault tolerant quantum computing. And the way that works, if you're familiar with classical error correction algorithms, what you do is you take a bunch of qubits, what we call physical qubits. Maybe you take 100 qubits and put them together. You put them together in a specific code such that those 100 qubits will create one logical qubit. And what that does is that it gives you some amount of redundancy. So if one or two of those physical qubits uh, fail, those operations fail, there's still enough redundancy so you can figure out what the failure was, and then you can correct it and move on with your calculation so that there's no error in the logical qubit. Now, the way you have to do that is uh, you do the operation, and there are certain measurement qubits that are in those 100 qubits called, the term is ancilla qubits. And by looking at those ancilla qubits, that will show you what the error is and where it is, but it's not necessarily easy to figure out. So what you need classical, and this is figuring in the what error occurred. You measure the ancilla qubits. That will give you a certain pattern of ones and zeros, but then you have to figure out, okay, where's the error, and that requires a very, very powerful classical computing. Riverlane is a company that actually supplies an ASIC. Some companies do it with FPGAs. Some companies, Riverlane has an ASIC that does that. NVIDIA, of course, is saying people, well, we have NVIDIA GPU programs that will do that. You figure out what the error is, and then you send new gate operations to those 100 qubits to fix the error. And you want to do that very, very quickly, and in order to proceed with your calculation. So that's that's what Riverlane was talking about is, and you want to do that for many, many qubits, and you want to do it very, very quickly. And that's measured in millions of operations that you need to do with the Riverlane ASIC.
So this one says, thank you, Doug, for your insights. For harvest now, decrypt later, I've read that this is a very real concern, but I've also seen that quantum computers will only be available to necessary end users. How would bad actors get their hands on these advanced technologies, open source, buy to use? Are developers working on certain codes that bad actors may use to extract personal information that can be blocked?
Yeah. So, stick with the current computing. There's RSA, there's elliptical curves. One of the bad actors, of course, is foreign governments. So many, many foreign governments, including unfriendly governments, have their own quantum computing efforts. And they're not going to go to an IBM buy the computer. They're developing their own, and we report on all those things also. Um, for we'll call it run of the mill hackers. Uh, I think they may not get their hands so easily on a quantum computer. These machines are going to be, typical cost today of a quantum computer is $20 million to $60 million. That's not something that people have, sitting in their bank account. Um, but again, where there's a will, there's a way, and there's certainly eventually people will have these powerful quantum computers that will be able to break RSA and elliptical curve. So, in order to solve the problem, what is needed is a full revamp, a remediation of the IT communications infrastructure. And all the places where people use RSA to pass keys, this is called quantum key distribution. Um, the good news is that there are now algorithms. There are new algorithms. RSA, for example, is based on a one-way problem of factoring a semi-prime number. And that's a problem that is what's called a mathematical one-way function. You can take two prime numbers, two large prime numbers, of maybe 1,000 bits each, multiply them together, and a computer can, of course, calculate that in microseconds. But taking that a semi-prime number and figuring out what were the two prime numbers that were multiplied together to get to it, that's the thing that takes millions of years and is intractable right now with a classical computer. So that's the thing a quantum computer would be able to do. So what NIST has done, NIST is the U.S. National Institute of Standards and Technology. They said we need new algorithms, and in 2018 they put out a call. They said all cryptographers around the world, send us your proposal for a new algorithm. And they went through a 5 year, more than 5 years, 6, 7 year evaluation process. And last year they said, okay, we found, we are certifying, I think 4 or 5 algorithms that you can use for encryption as well as something called digital signatures. And they tested these algorithms, as well as people around the world. It was all open source. They said who can break them, and it turns out many of those 69 algorithms, very smart people, clever PhDs, were able to find programs that could break those. They also wanted to select algorithms that were efficient, that the key size was reasonable, and the amount of computation that you did to generate the keys and decrypt the keys were thing. So right now, the recommendation, again, from the U.S. government is to implement those 4 or 5 algorithms, and the initials or the acronym used is PQC, standing for Post Quantum Cryptography. And that's where, again, I would recommend that any enterprise start their their remediation program. And yeah, of course, you have to start with planning, and that's again where there's many companies that are around to help you. Now, I will point out, by the way, that that's what we call the software-based approach to solving the problem. There is also a physics-based approach where you can create a fiber optic network that shoots around qubits, what we call entangled qubits. That's called quantum key distribution. So for very high security applications, people might take a look at that. That's a different way of doing it, but it's also more expensive and more complicated. So that's also available for very high security applications. And there are a few people looking at that as the way of solving the problem too.
That's brilliant. I think that is a great place for us to end here. I want to really thank you so much, Doug, for this excellent presentation, and thank you all for attending. This has been recorded. It will be posted to the Computer Society's digital library in the video library. We will send out an announcement to everyone who signed up for this series, and we'll also be sending a short survey afterward. We'd love to get your feedback on this presentation and recommendations for future. Again, thank you very much, and thank you, Doug.
Okay, thank you, Steve, for organizing this, and thanks to all the attendees. I enjoyed giving it.